right, looking at alternating series here, this is another convergence test. We've talked about alternating sequences in the past. Alternating series is simply adding the terms of an alternating sequence, and they usually have, or not usually, they will have -1 to the n or a negative number to some n exponent. If I were to write out the first few terms of this, if I plugged in 1 for n, -1/2 to the first is 1/2. If I squared it, -1/2 squared is positive 1/4. If I raised to the third power, that would be -1/8, then positive 1/16. And the terms alternate signs, hence the name alternating series, and then it would go on forever and ever and ever. -1 to the n plus 1 doesn't change that. If I start with n plus 1, if I plug in 1, that's -1 squared. I'll start with a positive term, 1 over 1, and then they will alternate after that. So plug in 2 plus 1 is 3, -1 cubed is not negative, so -1 over 2 plus 1 over 3 minus 1 over 4. That is an alternating sequence. And determining whether an alternating sequence converges is pretty easy. The first way you could determine it is this little helpful fact. I don't know if it has a name, but if the absolute value of your series converges, then so does the original series. So a series like this, I would compare it to the absolute value series. So if I did -1 to the n over n squared, and I took the absolute value of that, well, that's going to eliminate the alternating aspect of it. So that would end up giving me the series 1 over n squared, which is a p-series with p greater than 1. So if you have a p-series with a p-value greater than 1, then this thing converges, which means the original series that I took the absolute value of will also converge. So therefore, this converges. Okay, good. Okay, good. So that's one way. Now, sometimes the absolute value series diverges. That does not mean your original series will diverge. Sometimes the absolute value will diverge, but the alternating series will still converge. So this little test only works if the absolute value of the series converges. Otherwise, it's inconclusive. If it's inconclusive, then maybe we'll look at the alternating series test, which states that if you have an alternating series, it will converge if and only if you start off, the terms have to approach 0, so the limit as n approaches infinity is 0, and your n plus first term is less than your nth term, which basically means your series decreases, or your sequence decreases. Now our textbook, this is something that kind of struck me funny, so I went ahead and put it in here. The textbook said decreases for all n. I disagree with that. I think that the only thing that matters is that if eventually your sequence decreases. So it may increase, terms may increase for a little bit, but as long as it ultimately decreases in the end, then that would be good enough for the series to converge. So let's do some convergence tests. Let's do this one. Before I do the alternating series test, I will always see if the absolute value series converges. Well, if I take the absolute value of this, that would give me, let's see, the absolute value of -1 to the n over n gives me your harmonic series, 1 over n, which I know diverges. That doesn't tell me anything. That does not mean that this series diverges. So that is helpless. That's no good. So now I'm going to go into my alternating series test, which first part of my alternating series test is that the terms have to approach 0. So if I eliminated the alternating series aspect of it, I have the series sequence 1 over n, and the first thing I have to do is check to see if my terms approach 0. So as n approaches infinity, do the terms approach 0? And they do. So that part's good. The next part is the n plus first term, a sub n plus 1, has to be less than or equal to the nth term. And if I plugged that in, it would be 1 over n plus 1. Is that always less than or equal to 1 over n? And if it is, then we would have convergent series, and this actually is true because the denominator here is bigger than the denominator here, meaning that is also true. Since both of those are true, we know that this series actually converges. So therefore, my series -1 to the n over n converges. Now, y'all may recognize that as the alternating harmonic series. It turns out the alternating harmonic series converges, however, the regular harmonic series does not. So there we go. Uh, let's try this one. Um, we have an alternating series with my numerator being -1 to the n plus 1. The sequence, if I eliminate the alternating series aspect of it, my sequence is just 1 over n factorial. So is it true, first, do my terms approach 0? As n approaches infinity, is 1 over n factorial 0? And it is. That's true. So I'm good with that. And then I need to see, are the terms decreasing? So is 1 over n plus 1 factorial going to be less than 1 over n factorial? And this denominator on the left side is bigger, so that is also true. Therefore, this sequence converges, or series converges. Well, the sequence does too, but whatever. Therefore, that converges. Nice test, isn't it? This is a nice test. I like this test. It's not too bad. The problem is deciding whether we need to use the alternating series test or a comparison test or limit comparison test, or if it telescopes or if it's geometric. We have a whole bunch of tools in our arsenal now. Let's try this one. Sine of n over n cubed. Well, this one actually doesn't fall into the alternating aspect. It will change signs ultimately because sine bounces between -1 and 1. But my series is going to start with sine of 1 over 1 cubed plus sine of 2 over 2 cubed, which is 8, plus sine of 3 over 3 cubed, which is 27, plus dot 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 dot. And sine of 2 might be negative. Sine of 3, I'm almost positive, is negative. Actually, sine of 2, let's see. No, that's positive. Sine of 3 is positive. Anyway, they ultimately will change some signs, but alternating by definition is each one alternates from positive to positive. You can't do like positive, positive, negative, negative. So what I'm going to do, try to determine if this converges, is I'm first going to eliminate the negative aspect of it. I'm going to take the absolute value of sine n over n cubed, and n cubed is not going to be affected by that. That's going to turn it into the absolute value of sine of n over n cubed. And I'm going to see what happens with this series. Well, we talked about sine graphs and sine series earlier. I know that the absolute value of sine of n has to be less than or equal to 1. And if we're doing the absolute value of it, it has to be greater than or equal to 0. So what I'm going to do is squeeze this. We're going to use the squeeze theorem or the sandwich theorem. Now I'll divide everything by n cubed. Divide by n cubed. And I'm going to see what happens on the left and right ends. Well, on the left end, what I've got is that's the series of 0, which definitely converges, because that's nothing but zeros. This one is a p-series. This is the series 1 over n cubed. That's a p-series with p equal to 3. And anytime your p is larger than 1, then that converges. And what I've done here is I've trapped my sequence between two convergent series. So if those two converge, then so will absolute sine n over n cubed. And I'm actually not 100% in love with the way I said that. We did squeeze it, but I'm going to actually go to the direct comparison test. I showed that the series in question is less than a known convergent series. So I'm going to say by direct comparison, I know that this also converges. So by direct comparison, extremely closely related to the squeeze theorem. By direct comparison, I know that my original series will converge. So sine n over n cubed converges. There we go. Sounded kind of funny as I was saying it, so whatever. All right, so that one will converge because I know that it's less than 1 over n cubed, which is a convergent series. Then we have, I think, one more that I wanted to look at. This is an alternating series. I have that negative 1 to the n. I kind of single out the non-alternating aspect of it, and we're going to look at that to see if this series converges. First thing we have to do is check to see if the terms approach 0. As n approaches infinity, does n squared over n squared plus 5 equal 0? And actually it doesn't. Top degree is equal to bottom degree, so we'll divide the coefficients and you get 1. That is not equal to 0. Therefore, this series diverges. Therefore, this whole series, negative 1 to the n times n squared over n squared plus 5, diverges. Good? There we go. So that is your alternating series test. There is a little bit more to it, but we'll talk about it in more detail later.